All right, let's go ahead and get started. I want to welcome you back to Unit 9. This is stoichiometry. And we've been talking about limiting and excess reactants. Last time we discussed an analogy. We said that if we want to have a peanut butter and jelly sandwich party, what we would do is we would figure out which is going to run out first, right? And that's going to determine how many people we're going to invite. So I think it was the bread that was going to run out first. And so that was our limiting reactant, or what's analogous to the limiting reactant. But let's go ahead and take a look at an example, a specific example involving limiting and excess reactants from the standpoint of chemistry. So here we go. For the reaction shown below, we've got 12 grams of copper 2 chloride reacting with 22 grams of sodium nitrate. And we want to know, first of all, what's the limiting reactant, and second, how much sodium chloride is formed. So really we have two questions in one. First, again, is which one of the two between the copper 2 chloride and the sodium nitrate is the limiting reactant? So that's our first question. And the second question is, how much of the sodium chloride are we going to form? So let me just make some notations here on the reaction itself so I can kind of remember what it is that I'm given and what I'm looking for. So let's start with the 12 grams of the copper 2 chloride and 22 grams of the sodium nitrate, just like that. Okay, so 12 and 22 respectively. And I'm looking for sodium nitrate, right? It says looking for how much sodium nitrate is produced. And I'm going to assume that they're going to want it in grams since they're giving me grams and grams of the copper 2 chloride and the sodium nitrate as well. So how would I approach this problem? Well, the first thing I'm going to do is I'm going to convert sodium nitrate, or copper 2 chloride, I should say, and sodium nitrate into moles. So that's going to start the problem right there. So I'm starting with 12 and 22 respectively, right? And I'm going to convert those into moles. So 1 mole of copper 2 chloride has a mass of 134.45 grams of copper 2 chloride, right? So this unit and that unit is going to cancel on the top, on the bottom. That unit and that unit will cancel. By the way, check my 135.45 and my 85.0 grams respectively for the copper 2 chloride and the sodium nitrate. Check that, okay? The next thing I'm going to do is I'm going to do what's called a mole-to-mole bridge, because now I've got it in moles, but I'm interested in how many moles of sodium chloride that I can get. Now you might ask, well, why don't you just go directly to grams? You can't do that. You've got to go through moles, all right? So first of all, let's deal with the copper 2 chloride and the sodium chloride. So the copper 2 chloride and the sodium chloride, right? So let's take a look at the reaction again. So here's the copper 2 chloride and here's the sodium chloride. So this is the mole-to-mole bridge right there. 1 mole of copper 2 chloride produces 2 moles of sodium chloride, right? So I'm going to put that into my reaction so I can get 2 moles of sodium chloride. Now, that's going to cancel with that, and I'm left with moles of sodium chloride. Not quite there yet. I'm going to need to convert that to grams. So to determine the molar weight of, or molar mass, I should say, of sodium chloride, I'm going to add up sodium and chlorine. I get 58.45 grams per mole. So now when I cancel this with this, I'm going to get grams of sodium chloride. So I've got 10.43 grams of sodium chloride. Okay? Let's switch back to our attention back to sodium chloride and sodium nitrate now, and we'll find out what the mole-to-mole bridge is for that. So we've got sodium nitrate here, we've got sodium chloride here, so here's the mole-to-mole bridge right there. So this time it's a 2-to-2 relationship. Now again, you might say, well, 2-to-2 is just 1-to-1. They're going to cancel. That was a waste of my time. No, it's not. Follow the technique. Follow the strategy every time so that you don't get lost. This cancels with this, and I'm left with moles of sodium chloride. One more step, convert to grams. This cancels with this, and I'm left with grams of sodium chloride. So now what can we see from this? What we can see is that 12 grams of copper 2 chloride produces only 10.43 grams of sodium chloride. Compare that to 22 grams of sodium nitrate producing 15.3 grams of sodium chloride. So first of all, don't make the mistake, whatever you do, of saying that sodium chloride is the limiting reactant. It's not a reactant at all. It's the product. The reactant is what produced that product, right? What produced that product. So the reactant then that produced that product, remember, is the copper 2 chloride. It produced only 10.43 grams of sodium chloride. Now, we know this. Since 12 grams of copper 2 chloride produce only 10.43 grams of sodium chloride, the copper 2 chloride must be the limiting reactant, and the sodium nitrate is the excess reactant. We also know, because we've done the calculations, that 10.43 grams of sodium chloride was produced, okay? 10.43 grams of sodium chloride was produced. So we answered both questions. We've now determined the limiting reactant. That was one of the important things we needed to do. But we also determined the amount of product, which is sodium chloride, that we were interested in, that was formed. So we would report our answer as the limiting reactant is the limiting reactant is copper 2 chloride, and 12 grams of copper 2 chloride produced 10.43 grams of sodium chloride. Okay? And we're done with that problem. That's all they asked me for. That's all I'm going to give them. Okay? So that's that. All right, what I want to do now is I want to take a look at something called actual, theoretical, and percent yield. Actual, theoretical, and percent yield. So let's discuss the meanings of these terms. The theoretical yield is the amount of product you predict you should get from the calculations. The actual yield is the amount you actually obtain from an experiment. The percent yield is the actual divided by theoretical times 100. So often in experiments, in fact, almost always in experiments, we don't get in the actual laboratory what the calculations tell us that we should get as a product. It's some number less than what we should get. You understand? Why is that? Well, there are 1,000 different reasons. It could be experimental error. It could be something's wrong with the distillation tube. There's not enough cooling. Who knows? It could be anything. The point is this. It just doesn't happen that you get 100% of what you should get. So we need a way of quantifying that, right? So in the previous example, let's say you get 9.26 grams of sodium chloride, right? In that experiment, you get 9.26 grams of sodium chloride. Now, so this is the actual yield. This is what you actually get. Now, you might say, well, the problem said I was supposed to get this amount, 10.43 grams. Well, remember, you're not always going to get what you're supposed to get. Remember that from your calculations, you determined that 10.43 grams was the amount you should theoretically get, right? So that's how much you theoretically should have gotten, but you just didn't get that amount, right? It just didn't happen. So that's your theoretical yield, right? The 10.43 is your theoretical yield. So we're left then with percent yield. So remember that percent is the actual amount, the actual yield in grams, divided by the theoretical yield times 100. So once again, we actually got 9.26 grams, but we were supposed to have gotten, theoretically, 10.43 grams. That's going to be multiplied by 100, and we've got an 88% yield, okay? An 88.8% yield for this procedure. All right? So I hope that makes clear actual, theoretical, and percent yield. Actual, theoretical, and percent yield. All right. Now, the following problems are for AP students only. Let's take a look at this problem right here. It says, identify the limiting and excess reagents. By the way, reagent and reactant's the same thing for our purposes. When 25 liters of nitrogen reacts with 25 liters of hydrogen at STP. So we're going to learn some things here now because we haven't done a problem like this before, but now we're going to learn. The question is, how many liters of ammonia gas are formed? How many liters of ammonia gas are formed? So I'm going to put a question mark right here. Question mark, liters, just like that. Now, again, they're telling me I've got 25 liters of nitrogen. So 25 liters of this reacts with 25 liters of this, just like that. And they say that this is happening at something called STP. So we need to define some things here. First of all, what is STP? STP stands for standard temperature and pressure. That means we've got 1 atmosphere of pressure and the temperature is 0 degrees Celsius. Now that's very important because at that temperature and pressure, all gases have the same volume, or at least 1 mole does. 1 mole of all gases at standard temperature and pressure has its volume. 22.4 liters. That's extremely important, all right? And it helps us a lot with these types of problems. So let's figure out how we're going to determine the amount of ammonia that's produced. So we've obviously got two reactants. So we're going to have to determine which one of these is the limiting reactant. So we're going to start with the 25 liters and we're going to convert that to moles. Well, didn't I just say that 1 mole of anything at STP has a volume of 22.4 moles? Sure. So that means that this unit and this unit are going to cancel away. I'm left with moles of N2. Now what I'm going to do is I'm going to do a mole-to-mole bridge. I'm going to go from N2 to NH3. It's a 1 to 2 mole-to-mole ratio. I should say from NH3 to N2, 2 to 1, right? You can go either way. So 2 to 1 moles of NH3 produced from 1 mole of N2. So now look, this is going to cancel with this, and I'm going to be left with moles of NH3. Just one last step. Let's get our answer in liters. We're at STP, so that means any gas, including nitrogen, hydrogen, or ammonia, is going to have the same volume. These two are going to cancel away, and I'm left with liters of ammonia. So now what I'm going to do is I'm going to multiply across, and then I'm going to divide, and I get 50 liters of ammonia. Okay? So that's one of the reactants and how much product they would produce. Let's take the other reactant, this time the hydrogen gas. So 25 liters of hydrogen over 1 times, it's 1 mole of hydrogen gas per 22 liters. This and this are going to cancel away, and I'm left with moles of H2. Now let's do a mole-to-mole bridge. 2 moles of NH3 produced from 3 moles of H2, right? 3 moles of H2 to produce 2 moles of NH3. So there it is. There's the bridge right there. So I'm going to multiply that by that, and I get moles of NH3. Let's take one more step. Let's go to liters of NH3. I'm at STP, so 22 liters of any gas, including ammonia gas, is 1 mole. So now we're going to multiply across, divide, and I get this number, 16.67 liters of NH3. So I either produced 50 liters of ammonia or 16.67 liters of ammonia. Which one was it? Well, it was the lesser of the two. So this is the amount of product that I'm forming. This is the amount of NH3. The 50 liters is irrelevant at this point. And I also know that 25 liters of the H2 was what it required to give me 16.67 liters of ammonia. Okay? So since 16.67 liters of ammonia is less than 50, H2, the second one, must be the limiting reactant, and 16.67 liters are produced, at least theoretically, right? At least theoretically. Now, what if only 13.32 liters of NH3 are actually produced? What's the percent yield then? We're looking for percent yield then. So we're going to say the actual yield, what was actually produced, which we determined was 13.32, okay? 13.32 liters are actually produced, divided by the theoretical yield, which we determined to be the 16.67 grams, the lesser of the 50 and the 16.67 grams, was the theoretical yield, right? So actual divided by theoretical times 100 is going to give us this value, 79.9%. 79.9% then is the percent yield for this problem, okay? Folks, I've determined the limiting reactant, and I've determined the percent yield. That'll do it for this problem. I'll see you on the next screencast. Thanks. Bye-bye.